In today's lesson, we're going to continue our study of probability by moving into random variables and probability distribution functions. With that said, this is kind of a new chapter. This is going to be something new, so let's all take a deep breath and get ready for that. All right, we've got this. Let's go ahead and move into this new stuff. As you're aware, lots of times when we start a new thing, we need to begin with vocabulary, and so I've got some new vocabulary for you. There's a lot here, but it's really not super complicated. So first is the idea of a random variable, okay? And a random variable is just a quantity that can take on a variety of values depending on chance. In this particular chapter, we're going to be learning about discrete random variables. Okay, and a discrete random variable is a random variable whose values are discrete, and it doesn't sound very helpful. And what it means to be discrete is it means that they are individual and separate from one another. In math, the opposite of the word discrete is the word continuous. We will at some point later in the class learn about continuous random variables, but for right now, we're talking about discrete random variables. So to try and give you a little bit better sense of this, I'm going to go through a couple of examples of what discrete random variables might look like. So the first one, the random variable s could be the size of shoes worn by students. So you'll notice over here, like shoe size is something that is individual and separate. So you maybe you wear a 4, maybe you wear a 4.5, maybe you wear a 5. It's not like you wear like a 5.12473. Like there are only so many sizes of shoes, and they're all separate from one another. Okay, the random variable d could be the roll of a standard six-sided die. So you could, 1, 2, 3, 4, 5, 6. All of those results, all of those outputs of the random variable are things that are individual and separate from one another. Okay, the last example is one, and I just kind of wanted to show you, a discrete random variable doesn't have to have some defined endpoint. It could go on for a long period of time. The random variable L could be the number of lightning strikes in an hour. There could be 0 lightning strikes, there could be 1, there could be 2, there could be 3. In a really wild storm, there could be 100 or 5. There just need to be an upper limit for the thing. What's important for a discrete random variable is that they are individual and that they are separate from one another. Okay, so these are all examples of discrete random variables. Okay, so now I'm moving past that into the next thing. Okay, if we know enough about a random variable, we can actually make a table of all of the possible values and all of their probabilities. But to do that, we're going to need some notation. And so I kind of want to point something out to you guys about notation. Random variables are generally denoted by a capital letter. So you'll notice up here, I called these things capital S for shoes, capital D for die, and capital L for lightning strikes. There doesn't have to be a rhyme or reason to the letter that you use. What's important is that generally we use capital letters for random variables. Okay, now the values taken by that random variable are generally denoted by the corresponding lowercase letter. So if you were asking about the probability of somebody wearing a size 4 shoe, it would be small s being 4. So the capital letter is for the random variable for sort of all the possibilities, and the lowercase letter is when you're talking about individual occurrences within that random variable. We're now going to move in and look at some examples of how we might use random variables. So we begin here with what I think should be a fairly simple thing. Complete the table below for a fair four-sided die. Okay? You'll notice that in this table, up in the top, I have the lowercase letter x. And remember, we mentioned on the previous page that the lowercase letter generally represents sort of like individual outcomes, right? So if you had a fair four-sided die, the 4 things on it would be 1, 2, 3, and 4. So if we were going to fill this out, we'd put a 2 here, because that's one of the possibilities, and a 3 here. Now the bottom, and this might look a little bit complicated, but I'm hoping I can help us make sense of this. This thing is just saying the probability that x, the random variable, equals lowercase x. So the probability that the roll of the die is x, which could be 1 or 2 or 3 or 4. On the bottom, I'm just putting the probabilities that correspond to those numbers that are up on the top. Right? So since it's a fair four-sided die, all of these are going to be 1/4. Okay, you'll notice, by the way, that all of these things here added up to 1, and that makes sense. Remember that the sum of all probabilities in a space should be 1. Okay, so now let's ask some questions about this and make sure that we're understanding what this is saying. So first, what does the capital letter X represent here? And I mean, like, pause the video, think about it for a second. Like, what does capital X represent? Hopefully you understand that this represents the random variable which effectively represents the score that you would get on this four-sided die. So if capital X is the whole random variable, then what does the lowercase x represent? Hopefully you understand that the lowercase x here represents any individual one of these scores. So x could be 1, or x could be 2, or x could be 3, or x could be 4. Okay, so now moving further into notation, what does p of x equals 3 mean? Okay. Well, hopefully you understand that what this thing is saying is it's saying the probability that capital X, the probability that the random variable is 3, this thing is asking, this thing is basically saying what is the probability that the score is 3? Okay, so now what's the value of p of x equals 3? Well, looking in our table up here, it's really clear that the probability of getting a 3 is 1/4, so this would be 1/4. And then in the last one, what does the probability of x greater than or equal to 2 mean? Well, this would be the probability of getting a score of 2 or higher. Okay, so that means I would need to add up all of these things going on here. This would be 3/4. So 3/4 is the probability of scoring 2 or higher. So hopefully that made sense. This example was supposed to be really, really simple and really a chance to sort of talk about this notation and what it means and how we use it. So in this next slide, I'm starting with a key point that I know I already mentioned earlier, and that's the idea that the sum of all of the probabilities in the probability distribution function must be 1. It shouldn't be surprising to us. We know that all probabilities are supposed to add up to 1 when we look at a total probability in a distribution. So anytime you have a probability distribution, those things have to add up to 1 because it has to account for all of the possibilities. Okay. So I've got this example. Consider the probability distribution given below. You can tell clearly that I'm going to be talking about the random variable capital S, and so lowercase s is going to correspond to things. So it looks like this random variable is representing whole numbers going from 1 to 7. So I want you to sort of think for a minute, what could this probability distribution represent? And there's lots of correct answers here. And if you're up for it, pause the video, see if you can sort of write in proper mathematical notation like what capital S represents. So given that this is an IB course, I tried to make it something helpful. In theory, this could be a 7-sided die, but in this particular case, I thought about this as IB exam scores. And what I used here is actually the scores on the English higher level exam from 2020. And so I'm going to go ahead and write that here. Okay, now next question. Okay, so it says, what is the value of x? Well, x is right here. Okay, how am I going to figure out what x is? Hopefully you guys recognize, we know that all of these probabilities have to add up to 1. So if I add up all of these probabilities and set it equal to 1, I can solve for what x is. So I don't need to include the zeros that are down here at the end. So 0.02 plus x plus 0.46 plus 0.21 plus 0.04 equals 1. So if I combine all these decimals together here, this gives me 67, 71. So this is like 0.73 plus x equals 1. So it looks to me like x is 0.27. And now finally part C. What is the value of p of s greater than or equal to 4, and what does it represent? So pause the video, think about this one for a moment, and then come on back and let's take a look at it. So p of s greater than or equal to 4 basically means what's the probability that the score was greater than or equal to 4? Or another way of saying that is what's the probability that a student passed? Okay, so all I would need to do is add up all of the scores that were 4 or greater. Okay, if I add all those things up, we're going to find that this is 0.02 plus 0.27 plus 0.46. Oops, just realized I actually don't want that one because that was the 3. Plus 0.21 plus 0.04. Sorry, my work got messy there. If I add all those things up, I'm going to wind up with 0.98. Okay, and so a way to interpret this is that 98% of students passed the English IB-HL exam last year. So this, again, is a fairly straightforward example of what a probability distribution function might look like and the sorts of things we may be able to interpret from it. Now, it's worth noting that probability distributions are not always given by tables. very often they'll actually be given by a formula. Okay, so this thing I'm going to do here isn't really a full example. It's just kind of like the idea of what it would look like. So what if you were told this, right? That P of big X equals little x equals x over 10 for x weird looking E, which means is an element of the set 0, 1, 2, 3, 4. And so what the heck would this thing mean? Right? Well, this thing here is telling you what x can be. So it's effectively saying x could be 0 or 1 or 2 or 3 or 4, and that's little x. So the values could be those things. Now remember, little x is supposed to represent values that the random variable could be. So we could start by saying, what is the probability that the random variable could be 0? Well, according to my formula, it's supposed to be x over 10, so it's supposed to be 0 over 10. So the probability of the random variable being 0 is 0. Right? What about p of x being 1? Well, this formula right here tells me if you want the probability of the random variable being little x, you just plug it into this. That's going to be 1/10. It should be fairly simple. I mean, you guys could very quickly, I hope, tell me what the probability of x being 2 and x being 3 and x being 4 are. Right? These should be 2/10, 3/10, and 4/10, right? And in a lot of ways, we can sort of double check our work here. These things all better add up to 1. Because if my probabilities are adding up to more than 1 or less than 1, I'm missing something. So the whole purpose of this quick little example here was to show you that sometimes you won't be given a table, you'll be given a formula. If you like tables better, cool. After you make this formula, after you use this formula, feel free to set up a table. Right? You can put little x on the top. You can put p of x equals little x on the bottom. 0, 1, 2, 3, 4. You can take all of these values and put them into a table. And now you can see it as a table. If that helps you, great. What's important is that you need to know how to use these formulas to generate the table and come up with the probabilities. So I'm hoping that this next example is actually going to be fairly straightforward. It says consider the probability distribution given by P of y equals my for y being a part of the set 1, 2, 3. Find the value of m and construct a table for this probability distribution. So I would really encourage you guys pause the video and sort of try the beginning of this one on your own. Maybe try what you think it should be, and then watch a little bit of the video and see if you were right, and then see if you can sort of piece together how to do this. We're being asked to find the value of m, which means you're going to need to set up some kind of an equation and solve. So best of luck. So what I'm thinking here is there are 3 possible values for y, and I have a little formula for what they should be. Let's compute what's the probability y is 1, the probability that y is 2, and the probability that y is 3. Those are the 3 things it could be. Okay? Now when I do this, I'm not actually going to get numbers. I'm going to get expressions. When I put in 1 to this equation, I'm going to get m. When I put in 2, I'm going to get 2m. And when I put in 3, I'm going to get 3m. But what I know is that these are the only things that y could be, which means what do these 3 things all have to add up to? They'll have to add up to 1. So 6m has to be 1, which means m has to be 1/6. And now that I have that, I can go back and figure out that these probabilities are 1/6, 2/6, so a third, and 3/6, so a half. The problem then said construct a table for the probability distribution. Cool, this should be real straightforward, right? The top row in this table is going to be little y. The bottom row will be the probability that big Y equals little y. And then in my table, I just have to put in the values it could be along with the probabilities of those things. That's all there is to it. This is all you need to do in order to use a formula for a probability distribution. And here I have the last example of a random variable and a, not really a random variable, but more the idea of a probability distribution. Okay. In this one, I'm not going to give you the full table, and I'm not going to give you a formula for it. You're going to have to do some probability work that you already know how to do to come up with this table. Okay, so this example says, let T be the number of coins that turn up tails when 3 fair coins are flipped. Construct a tree diagram and use it to find and complete the following table. Okay, I suppose we don't really need to find this table. We just need to use it to complete the following table. Okay, So I need to make a tree diagram. I'm flipping 3 fair coins, and it looks like what I'm really counting are tails. Okay, so when I flip that first coin, what are my possibilities? It's either tails or it's heads. And the probabilities of these things are a half and a half. Okay? If you feel like you can do this one on your own, I'd say pause the video, try it. If you're really, really worried about it, you can follow along with me. But this is a decent example for you to be able to try on your own. The next coin would be represented here. I could either get tails or I could get heads. And I could get tails or I could get heads. And again, each of these things are a half. And then the third coin flip, this is starting to get tight on space here. It could be tails or heads, tails or heads, tails or heads, tails or heads. And all of these branches here are a half. I don't know that I have enough room to be able to put a half on all of them, but all of these guys all the way down are a half. Okay, what do we do at this point now that we have this much tree diagram? Do you guys remember? Hopefully remember that you multiply to the end of the rows, right? So the top row, tails, 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 it's a half times a half times a half. This is going to be 1/8 up here. In fact, if we think about it, every single branch in this thing is 1/2. So every time I'm going to do a half times a half times a half, half times a half times. It doesn't matter where I'm going. All of these branches are going to be 1/8. Okay, so every one of these 8 branches are all 1/8. Okay, now what I have to do is I have to go back and think here, right? What they gave me in the table is they said, like this thing here, what does this represent? When you think about that for a moment. That represents what's the probability of getting 0 tails? And the problem said it should be 1/8. Well, if I look at this, the 0 tails would be getting heads, heads, heads. The only way to get 0 tails is to wind up down here, and that's 1/8. Okay. Now next, I'm going to use a different color for this one. What about the probability of getting 1 tails? Where could that happen? Well, I could get tails, heads, heads. That would be one of them. I could get heads, tails, heads. There's another one. Or I could get heads, heads, tails. There's another one. It looks like there's 3 ways that could happen, so this will be 3 out of 8. Okay, if you haven't done any of this on your own to this point, pause the video here, make sure that you can get the last 2 on your own. This time I'm going to switch over to a black pen. So for 2 tails, it could be tails, tails, heads. There's one of them. It could be tails, heads, tails. There's another one. Or it could be heads, tails, tails. Those are the only places that happens. Okay, so getting 2 tails, it looks like there's a 3 out of 8 chance. And then finally, for the last one here, I could possibly get 3 tails. There's only one way that happens. Tails, 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 1 out of 8. Okay, so we've completed this table. And then the very last thing, determine and interpret the value of the probability of t being greater than or equal to 1. Remember, what does t represent? T represents the number of tails that we get. So this question is really just asking, what's the probability that I got at least 1 tails? Well, to answer this question, I just need to add up all the things that are 1 or higher in my table. This is going to be 7/8. Okay, so we have a 7/8 out of 8 chance of obtaining at least 1 tails. And really, that's it for our introduction to discrete random variables and to probability distribution functions and tables. We're going to be doing a lot more stuff with this over the course of this short chapter, but this is our intro. So best of luck as you guys work through the exercises.